folks. I am having a slight technical difficulty. Okay. I think we're good. Apparently my Google Chrome had a slight issue I had to fix. For those of you who have not been with me on this before, you'll notice my face goes all over the place because I have about 8 different screens up to make this happen. Hi, Duncan. Can you tell me if you can hear me okay? Hi, Brandy. Hi, everyone. So, let me pull up my chat box. Hopefully you guys can see everything okay. If you can't, I need you to let me know. There's about, okay, my hand might have actually just been laying on top of the speaker. I'm sorry. Can you hear me okay now? If I talk my normal voice? I'm also on line with the support for Google because my phone died today. It started smoking when I plugged it in to get charged, so alright. Brandy has me on the big screen so you can hear me and see me great. Fantastic! Well, go ahead, and if you have any questions, now's the time we can answer them, hopefully. I have this, oh, let me pull this up, hold on. I want to do my chem sketch. There we go. So the way that this works is you can ask me questions and I can draw things, and then if for some reason we need to do a mechanism, it can be kind of cumbersome to do it on chem sketch. It just takes a while. So I'll switch over to paint and then we can paint stuff. So, with that said, feel free to ask me questions. And remember, there's like a 15 to 20 second delay. And the delay is not even consistent. It depends on your computer, apparently. We found that out last summer. Pyridine is aprotic or protic? You're not going to like the answer on that one. That one's going to depend on the pH. So, for all intents and purposes, we'll consider that one. Sorry, we'll consider that one protic because it can take a proton. It doesn't really have one to give. I feel like that's too tiny. Can you guys see that? I might need to make that bigger. Okay, so this is the structure of pyridine. That can become protonated though. And give us something like that. So technically, because it's an acid-base situation with a weak acid conjugate base kind of thing, yeah, I'm going to say it could be protic. Is it still too small, Duncan? Can you see it okay? other questions? I'm sure that wasn't the only one, right? Well, I'd be willing to do one. What would you like me to do? I'm waiting to see if Duncan answers me back. So, yeah, Duncan, I can do a Gilman reagent question, just like, yeah, we can talk about that. And then Mackenzie, transition states, should we know? Basically, you should be able to determine any transition state, because if you know the mechanism, you should be able to determine that. And then Lauren, honestly, I haven't looked at that old exam since I wrote it over a year ago, so I don't know how similar it is to the old test. It has a page of nomenclature, it has a page of reactions, it has a page of mechanisms, and it has a page of other miscellaneous information. That's generally the format for all my exams. Okay, so Duncan, if you have let me switch over to the paint so we can show it easier. So let's say we have some sort of Gilman reagent. So you've had to make that using, you know, lithium and copper, and you use these different components to make something that essentially comes out with copper attached to some sort of R group, okay? And it should be symmetric. That copper has a negative charge on it, and it gets complexed with lithium, which is why you usually see it as Cu and Li, you know, together. We can put that with some sort of carbon that has a good leaving group on it. The ones that we've seen for this example are alkyl halides. So let's say I have cyclohexane. That's a really bad cyclohexane. Let's say we have cyclopentane, since that's what my brain wants to try and draw apparently. And let's make that with iodine. Okay. So what I can do is remember that the carbon that's part of the halogen, right, these are essentially carbanions, right? So this here, whatever that R group is essentially a C with a carbon with a lone pair of electrons and a negative charge on it. So what we can do is show that attacking at a place very comparable to the SN1, SN2 type reactions that we've done, and displacing the leaving group. And so when you do that, you would get whatever that R group is, and that R group's going to be a carbon group, right? That's the type of chemistry that it does. You have to use lithium, and then you use copper iodide to make this guy to begin with, and we did that one in class. But yeah, essentially, and it's the same way with the Grignard reagents. Those organometallics are very similar. Remember that whatever this R group is here is essentially the same thing as this. And you can use the mechanism in the same exact way you would use that. Here, let me give you another example. Oh, wait a second, I bet Google's probably trying to talk to me. going to send me a new phone. Do I need to send back my old phone to you? Yeah, so I literally plugged my phone in today in the car on the way home, and I was using it, emailing one of you guys back actually, and it started to smoke. Cell phones are not supposed to smoke. So, anywho, okay. So, Duncan, let's do one more of those, okay? Let's be very specific about this, all right? So, I'm going to go ahead and give us, how do I want to do that? I swear this looked better just a second ago. What was I doing? Okay. That's... Apparently the pencil function works better than the pen function. Okay. So in this case, let's use like an isopropyl type group complex to the carbon. So this here is going to be our Gilman reagent, right? So, Lauren, they're not actually bonded together covalently, which is what we're usually thinking of in this class. They're ionic. Okay, so those opposite charges are holding each other together. So, anyway, our group in this case is going to be that. Okay, attached to something. And then let's just put this with something small, like a methyl group. Okay. There we go. That'll be easier to see. Now, remember that the group that looks like this, because it's attached to the copper, it's going to be a carbanion. So we can actually show the bonds here. I'm trying to like bold that, or here, whichever one you want, because it's symmetric. You could do both, okay? Those are going to reach out and attack because they're actually a really good nucleophile. It's completely different chemistry than what we're used to seeing, because we're used to seeing stuff that's not metals, but metals have different chemistry than what we're used to seeing. Then we spit that out. And then, let's see, Duncan, can you tell me what the name of my product will be? Think about it. One methyl butane. I don't know, let's see. So we'll have that same, put that back. We had that, right? And attached to that is going to be the methyl group. So yeah, that'd be 2 methyl butane, right? Did I do something wrong, or did you do something wrong? Oh. I added an extra carbon, didn't I? No, I think I added... Duncan, you were right. I added an extra carbon. Look, that's... Let's draw that out. It would look like that, right? So now when we add that part together, It's now going to be put with a methyl group. So that would actually be, let's see, 2-methyl propane or tert butane. If you wanted to call it that, that would be the same thing. I'm ashamed of us, Duncan. We knew better than that. Equivalence of lithium and alkyl halide. We take off on the exam if we get that wrong. If I asked you to balance the equation, Melissa, and yeah, but I generally, most of the organic chemists in the world don't really do that a whole lot. I showed it in class just to make sure you guys could kind of understand where all those were coming from, because it would be kind of hard to visualize it if you didn't have all those stoichiometric coefficients correct. It would be like, where did all this come from? But yeah, I'm not terribly concerned with it if you leave those off. What was the name of the structure again? Brandy, I'm assuming you're talking about the one I just had. It would be 2-methyl propane or tert butane. Oh, the guy from Google thinks that I'm on a review session with my professor. He's like, oh, good luck with your class. Because I told him I'm sorry it's taking me so long. Can we go over the exam I posted from last fall? The whole thing? Because that'll be kind of hard to do on here. Do you have a specific question, Melissa? Yeah, I see that. Can you still hear my audio? That's really weird. Let me... Melissa, let me relaunch this real quick, because... How weird. I wonder if I switch. That is bizarre. Okay, well, I don't want you guys having to like stare at my weird face like that. So I'm just going to turn the webcam off for now until I can figure out what's going on. So how do I do... Okay, old exam. Let me see. So Lauren, now I'm actually going to look at the old exam. So this is 3520 exams. Was it fall 2016, I guess? That sounds right. So there's a issue with this program that I'm using. Actually, it's an issue in Word, in that it does not allow Word images. Like it won't use window Word to pop up in one of the windows. It's real stupid. So if you're like, why can't she just show us that? I wonder if it'll come up in Paint. Okay, guess I can use it on there. So Paint is going to be the way to go for this. Let me switch back over. Okay. Can I get some confirmation that you can see that okay? Anyway, so in this case, Melissa, the answer is actually very easy in that you know which one it's going to do. Can I make it a tad bit bigger? Hold on, Duncan. I'm working on it, buddy. The carbon that is the halide is attached to tertiary. Yes. Yes, yes, yes. Okay. Sorry. Oh, for the love of goodness. I may or may not be able to make it bigger. No, I can't. I'm sorry. Anyway, this is the first mechanism on the third page. Melissa, I'm hoping that this is the one you were talking about, where I have the bromine. Okay, where I have the bromine. And so what I was going to say is, this one's actually really easy. You know it's going to do the substitution reaction because I show you which reaction it does. So, you know, if you were to, grab my pen here. So let's say I have the same reaction, but I say that instead of that being the product with the NH2, like that, that's a really bad NH2, I'm sorry. So, right, the elimination product would be much different than that because it doesn't have a double bond anywhere, right? So we would end up with, let's see, one of the products would be there. And then we would have another one there. Now the question is, which one's major and which one's minor? And you might remember me saying this in class, I don't know, but I do my best and it doesn't always work. Left is major, right is, we got Duncan. Yep, one on the left. You guys both got it, awesome. So I try to only grade you guys on like one principle at a time. It doesn't always work 100%, but I try. And so, yes, Brandy, you got it too. Everybody gets a star. Here, I'll put a star. Yay! And so for mechanisms, I don't give you guys an open reaction where I don't tell you the product. So that way I can just grade you on a mechanism so you know which reaction I'm talking about. And then I give you, you know, a whole separate page of reactions. So that's, in general, how I always do every exam. It's pretty consistent that way, so hopefully that makes sense. And you guys all did. You got it all right, so good job. And please, somebody let me know if my... Oh, no, it's still absolutely frozen. So for the mechanism, since it's SN2, well, so let's look at it. Is it SN2, right? So look at the functional group here, or the carbon that the leaving group's attached to. Which is that? Primary, secondary, tertiary, or what is that? No, Melissa, we didn't cover it yet. We'll get to it later. This here's a tertiary carbon, right? I'm trying to write that as tiny as possible. It's not working. That's a tertiary carbon, though. Yeah, so it's going to be SN1. Now, in this one, I didn't show any stereochemistry or anything like that either. But because it is a highly... I mean, it's even more highly sterically hindered because it's sitting right next to that gigantic benzene ring. But yeah, that bromine will pop off first, and so it'll be a stepwise mechanism. I'm actually using my hands to try and describe this, and then I just remembered you guys can't see me. Shoot, there we go. I'm going to give you guys one to work. When we were in class the other day, we didn't get around to doing much of the problems from chapter 10. Oh goodness. Something else that's a complete pain in my side is that Kim Draw does not work with this technology either. Kim Sketch does, and Kim Sketch is much more difficult to use. So what I want you to do is figure out what all we need to put together to make this using Grignard chemistry. And then let me pull that window up. What is this? Okay. And then Melissa, that is a really long mechanism and it's difficult to show on here. I will try. And then, Mackenzie, I can definitely give you another example of one of those. So, those of you who want to work on the Grignard reaction up here, that's fine. I'll go over that in a second. Let's see, I'll have to... Yeah, that's not helping either, is it? What did I do to my hair while you guys weren't able to see me? Sorry, I talk a lot with my hands, and then when the video's not there, I feel stupid because I still keep using my hands to talk to you guys. I'm like, you can't see me at all. Okay, so, all right, Melissa, let's do this thing. It is a challenging mechanism, but that's okay. Just need to pull up the right screens here. Okay, so in general, and you know what, because this is, no, that's gotta work. All right, so let's do something where we can tell whether it's Markovnikov or anti-Markovnikov. Okay, so the simplest that we can really do is just adding in basically propene, because it's definitely going to have a Markovnikov and anti-Markovnikov product possible depending on the reaction conditions. So you're talking about doing the oxymercuration reaction, and so in that one you use some sort of mercury. I was getting ready to type out mercury instead of HG. Look at me. I swear I'm a chemist. Mercury In some cases, you'll see examples using mercury sulfate. I think in your book, though, the only one that they do is mercury acetate. Okay, so that's generally shown as that. And nucleophile, taxi, electrophile. Well, you know, if you have something that's an electrophile, we talk about things being positively charged, things like that. Well, a lot of metals are going to be a decent electrophile. So here we go. Nucleophile, taxi, and electrophile. The leaving group leaves. But then at that same time, what that would give us, and don't write this down yet, but that would give us something like this. Okay. That's supposed to be a hydrogen. This is kind of hard to do, I'm sorry. My screen's not calibrated. Okay. Well, so the thing is, though, is that you would end up with a positively charged carbon there. And so that mercury will come in and bind to that. Well, the thing is because they're all coupled right next to each other, the reaction basically happens all at the same time. So it's a concerted mechanism. So I'm going to erase that stuff since it doesn't happen that way and show you how we can show it. So that mercury can now bind, and you'll show that basically forming a bond with that carbon in the middle. In a mechanism very similar to what you see when we work with like halogenation using Br2 or Cl2 or one of those, you'll end up with this kind of weird triangular shaped intermediate with a positive charge on it. And then that's where water comes in. Water's a good nucleophile, right? And so in this case, it'll attack and displace the mercury. Okay. Now, that'll give you something like this. And then the mercury's still attached because that didn't go anywhere yet. Okay. So in general, that is going to be a very strong acid, and so it's not going to take a lot for a base to deprotonate that. I'm just going to use a generic B here. It could be water. It could be the acetate that we kicked off over here. Okay. But we'll deprotonate that so that we get our alcohol, but we still haven't taken off the mercury yet. And that's where we use a chemical called sodium borohydride. Borohydride has BH4 on it. It's a hydride donor. Remember, hydride is hydrogen like that. So essentially, it's going to come off, attack, and kick off the mercury. And then you get your product, which I don't know if I have enough room. Would essentially just be isopropanol. Okay. I'm sure there are other videos also on Dr. Google that have this particular mechanism, so let me make it kind of smaller. I told you, it's kind of a hot mess. This technology is really cool and it works for a lot of really neat things, but if you're having to do a lot of stuff, it can get really messy really fast, so I'm sorry for that. Let me go switch back to the text box. Okay. And then magnesium and ether. Yes, yes, yes. Duncan and Lauren, y'all are on top of it. So you'd need pentane, then you'd add magnesium to that, or the bromocyclopentane basically. You'd add some magnesium to that to make the Grignard reagent, and then basically any kind of proton source like water would be able to take that off and just make it into pentane, cyclopentane. Okay, And Mackenzie, I haven't forgotten about you, hun. Show us an example of an E2 reaction with a chair conformation. So, wait a second. Okay. So I think I'll actually switch back over to Kim Sketch for this. So I'm going to give us that one and that one, that. Okay. And then let's just be kind of generic here. We can use some sort of base. Like we'll just use hydroxide, that'll work. Do the elimination, okay? So I want you guys to work on this. You're gonna need to do the chair conformations. I will be right back. I need to run to the bathroom. Okay. Dogs everywhere. You lay down. Okay. Hi, Heath. Are you just wanting to let us know that you're here? Or oh, wait, I thought you were going to be at work. There should have been a good leaving group. Did I not give you one? There's a chlorine one there. Chlorine's a good leaving group. All the halides except for fluorine are good leaving groups. Sorry, I have so many dogs clicking around me. They had an interesting day. Well, that's great, Heath. I'm glad you made it. Yeah. If they were both methyl groups, then we'd be having a very different conversation right now, wouldn't we? We'd be like, I swear we haven't done this chemistry yet. What is she trying to do to us? But yeah, so basically these are going to be cis to each other, right? So on one chair conformation, it'll be where they are, where one, how am I wanting to say this? In both cases, they're going to be cis to each other, right? Flipping the chair doesn't change that. It just changes whether or not... My handwriting's really bad. I'm sorry. I know you guys are having to deal with my handwriting too. Like, I swear that says a methyl group. But so remember that when the chair flips, it goes from axial to equatorial. So I'm just going to kind of arbitrarily assign this. This will be my methyl group. We can designate that as Me. And then cis to that pointing up is my chlorine. Then when I flip that, the methyl is still pointing up, but now it's in the equatorial position. And the chlorine is still pointing up, but it is in the axial position. So what we need is we need to see if there's somewhere on here that has some sort of anti-periplanar hydrogen, right? So if you look at, let me pick up a color here. If we look at this molecule on the left, right, and it's the same molecule, right? These are conformational isomers. But if we look at the one on the left, that chlorine is not in the axial position, which is required for it to have an anti-periplanar hydrogen, right? So that means this one can't undergo any chemistry at all. Well, it could undergo nucleophilic substitution chemistry, but it couldn't undergo the type of elimination chemistry you're asking me about. So now I look over here, and I have one hydrogen, right? This is an alpha hydrogen, or alpha carbon, and this is an alpha carbon. They both have hydrogens that would be anti-periplanar to that chlorine, meaning they're basically parallel to each other, right? So that means you have two possible products, because in this case you have two anti-periplanar hydrogens. So I want you to work for a second. I'm going to take a sip of water. I want you to do both of them and tell me which one's going to be the major product and which one's the minor product. So, Lauren, how do we know the chlorine was equatorial? Well, if you remember when we are, let me see if I can, I'm going to scroll over here just to make a clean slate real quick, to make it kind of bigger. But if you remember back to organic 1, and I mean, that's a big if because some people remember it and some people don't, but when we have our cyclohexane, right, we have on every carbon there is an axial group coming off of it, 3 pointing up and 3 pointing down. On the ones that are pointing down, there's also groups that are pointing up, and those are considered equatorial because they go around the equator of the cyclohexane rather than straight up or straight down. Okay? The ones that are going straight up also have another group on them that's going to be equatorial, pointing down. So every single carbon, yes, Duncan, that's correct. So every single carbon on a cyclohexane has something coming up and something going down, but it's the angle at which they're doing that. So some of them are going to be straight up and down, and we call those axial. And if they're going out to the sides, kind of like that would be going up, okay? But going up out to the side rather than going straight up. So we call those equatorial, right? Well, when you flip the chair, everything that was pointing up that was axial is now still pointing up but equatorial. And everything that was pointing down axial is pointing down but equatorial, and vice versa. And so essentially, I knew that either of these structures that I drew, okay, the one on the left or the one on the right, both of those happen, right? So both of those pictures have the chlorine pointing up and the methyl pointing up. But in one case, the chlorine is equatorial, and the other way it's axial. And on the other one, the methyl's axial and then equatorial, okay? And those are in equilibrium with each other. That's just how chair conformations work. So essentially, you just have to know that pointing up, right, like the big wedge lines that I have here, those mean pointing up. And as long as you have your chair conformation where you have both groups pointing up in their, you know, right next to each other here, carbons 1 and 2, then you're going to be able to get that correct, okay? Now, let's see what our product should be here. If I lose this hydrogen here, we would end up with cyclohexene like that has a methyl group right there. And then another one, if I lose that hydrogen, where the methyl group is there with a double bond. So which one should be the major product and which one should be the minor product? And Melissa, there are no anti-periplanar hydrogens as fits in the equatorial position. That's why it would have to flip to the axial. You'll basically only ever see this with axial positions. I don't think I missed is by the methyl, this one here. So yeah, if you thought that the one that's on the right is going to be, yes, that's going to be our major because it's more substitute. Duncan, you keep talking right when I'm saying stuff. I don't know if it's probably delayed from when I say it. You guys are literally talking or chatting the same exact things that I'm saying as I'm saying them. So yeah, I hope that answers your question on that. Do you want to do another example, or do you want to do another example like this? Or do you guys think you got this good? So polite. Thank you, and a yes, please. Okay. So we'll be able to make this pretty. Give us our products here. Go ahead and fill this back in. Let's see, one case was this. The other case was that. And that was major, and that was minor. Okay, so let's do another one. If I have cyclohexane, and it needs some sort of leaving group on it, right? And so in this case, I'm going to do them where they are trans to each other. So let's make one of those a bromine. And then I've got my CH3 group here. And then get a little bit crazy here. Let's show a couple different things just for extra practice. So let's do an SN reaction. Let's do an elimination reaction. And And let's use for our nucleophile / base sodamide. Okay. Work amongst yourselves. Work with a buddy if you can, if you're with one. It's so strange, isn't it, how just seeing something one more time can sometimes do just so good. Dramatic pause. Cue intense music. You guys are ridiculous. Brandon, my students are being special. I'm going to check my email real quick while you guys are working on that and make sure that nobody's been emailing me trying to get questions answered. So here's a question. Are we going to assume this is undergoing SN1 or SN2 chemistry? Bimolecular or unimolecular? Yep. Correct. I agree with Lauren. So with an SN2 reaction, do you get retention of configuration? Or do you get inversion of configuration? That looks like a weird, like, Swedish way of spelling inversion, Duncan. Yes, inversion. It is a strong base. It's also a pretty decent nucleophile. Right, like hydroxide can be a nucleophile and a base. Bases by definition are nucleophiles, they attack hydrogens. So, since NaNH2 is strong, does that mean elimination is going to be favored? Yeah, sometimes. It probably depends on the solvent and the temperature. I'm really trying to discourage us from trying to pinpoint all those trends because some of those trends aren't as useful as you think they are. Heath, look at the handout I gave you guys the other day. I said we were going to do SN2 being for secondary carbons because your book does it that way too. But sodamide and ANH2 strong, does that mean elimination is going to be favored? In theory, yeah, but in actuality, you're probably going to get byproducts of the substitution reaction as well. So let's look and see what those would look like. And Sean, yeah, we'll do that one too. It's okay. Like, we're making assumptions, right? I mean, that's basically the best that we can do with chemistry. So I had my BRT there, and a methyl group here. So let's draw some chair conformations. Remember not to draw these as the double-sided resonance arrow because these aren't resonance structures. Now these are going to be trans to each other, right? Like the bromine's pointing back and the methyl points up. So if I always just kind of consider this one there, this one here. And when that flips, it's pointing straight down. So those are that's always my focal point. You don't have to use my focal point, but if you're always wondering why I do it the same way, so I can keep track of things, it makes it easier if you're always consistent. So if that bromine is pointing down, it needs to be pointing down. In either chair conformation, it will be pointing down. One will be axial, one will be equatorial. The methyl group is pointing up. Okay. So in this case, I have two alpha carbons, right? I have the one here attached to that, that spot there. And then I have that alpha carbon. Well, if you look here, and we can only, who was this? Was this Melissa or was it Mackenzie or whoever asked me? Right, we can't have antiperiplanar in the equatorial position, at the alpha position. So we can only do this when we're looking at axial positions. So that means we can't do anything when it looks like that, okay? I can only do it in this conformation. So now I have to look and say, well, where are my axial hydrogens? Well, in this position here, next to it, there is no axial hydrogen. There's a methyl group there. So even though that would give us, in theory, the more substituted alkene based off Zaitsev's rule, it can't do it because it can't undergo that type of mechanism. But if you notice, there is a hydrogen behind it there. So when the base comes in to deprotonate, those bonds will come down and kick the bromine out. So that means we can only get one product from this, right? In addition to the nucleophilic substitution product. So that would be, scoot, scoot, scoot. So my methyl group is still here. And then my bromine formed a double bond. So that's what we got. So if I go back to Melissa, count them. Those are beta carbons, not alpha carbons. Has to be in that next position over. What I want to show us is right there. And there. All right. So if we did this reaction, we would probably get mostly elimination reaction, but we could end up with some substitution byproduct, and so it would look like that. Okay. Now, Sean has joined us and had a question about number 8 from the old exam. Pull that back up in my computer. So 1, 2, 3. Sean, are you saying the 8th one down? Because I didn't number this one, I just did it in parts. So 1, 2, 3, 4, 5, 6, 7, 8. The one where we're going from an alkyne to an aldehyde? Let me know if that's the one you're talking about. Heath, it couldn't be an E1CB reaction because there's no beta carbonyl. Okay, so let me, for those of you, I don't know if you guys all have like the exam sitting in front of you or not, so I'm going to, why won't it let me? It just doesn't want to let me do what I want to do. So I must have used ChemDraw to write the exam, and then I used ChemSketch on this computer for this stuff we're doing tonight. Okay. I'll be right back, but I want you guys to think about the different situations that happen with alkynes. Look at enol chemistry. I'll be right back. So Melissa, you are correct. It is a borohydride hydration reaction. You don't need to give the enol product because it automatically converts to the keto form. And Sean, so you started with H2 and Lindlar's catalyst, which would give us the alkene. There are ways of converting alkenes to aldehydes and ketones through various oxidation reactions. but that's not one that is in our book, and not one that we've gotten to this point. And I know, I'm sorry, you were in a different class with a different book at one point, so you might actually know a way to do that, and if you do, I wouldn't count off for putting it down. But yeah, for this one, we have to do an anti-Markovnikov type of reaction on this, and the only way that the majority of students probably in class would know how to do this would be with borohydride, BH3 peroxide, and sodium hydroxide. And it's a one-step reaction. If those of you who are watching and you're like, what on earth is she talking about the enol? So when we have this weird intermediate, right, when we're talking about doing anything with alkynes where they have two different pi bonds that could be added to, right? So if you do like a hydrohalogenation, you have two hydrogens and two halogens. If you do a hydration though, you only add once. And that's because you end up with something called an enol. Looks like that. E-N-O-L, meaning an ene, that part here, alkene, ol, meaning the alcohol. So that's why they get called an enol. And they automatically shift in equilibrium, and the equilibrium, let me see if I can like bolden this to show you how serious I am kind of thing. The equilibrium heavily favors the keto form of this. It's called a tautomer. And the process of going from one to the other is called tautomerization. I'm not going to go over the mechanism with that one tonight, Melissa, because it's really, really long. I'll just tell you I didn't put it on the exam. If you want to go over it sometime this week, I'll be happy to go over it with you. But it's a very lengthy mechanism, and it's very difficult to show something that large on a screen this small. But yeah, if any of you guys want to come by and talk and learn more about that one, you can also look at them on the Google. I'm sure that the Khan Academy has a good video on it. But it's just the anti-Markovnikov reduction, sodium, well, my words, the borohydride oxidation. So the format of the exam is, for pretty much all my classes, is a page of nomenclature, a page of reactions with no mechanisms required, a page of mechanisms where I give you the product of the reaction and you have to show me the mechanism to get to it, and then a page of kind of other miscellaneous information depending on what we've covered in class. Oh, it's already late. It's 8:45. You guys got any more questions? Sean, did that answer your question at all? What did you do after you did the partial hydrogenation? I'm feeling good about this. Yes, Melissa, only aldehydes or ketones, so no carboxylic acids. Don't do those. And then yeah, so Sean, that would also work if you did the permanganate oxidation. That would be fine. And actually, we might have. That one might actually be in our book too, in chapters 7 or 8. But yeah, that would also absolutely, I would accept that full credit. Usually, and let me see if I wrote it on this one. I usually write, yeah, there may be more than one right answer. Because after you get to the point where you've done so many reactions, a lot of times you can have a couple different options that are all very good options, right? Very valid, good options. And I absolutely count all of them. Do we need to show intermediates on the exam or transition states? So I could ask questions about transition states, right? So transition states, remember that those are the, yeah, no problem, Sean, anytime. Remember that the transition states are the ones that are like, so here's an example of a transition, oh gosh, that looks terrible, of a transition state for an SN2 reaction, right? So like the leaving group is leaving, and then the nucleophile is coming in, right? And we put the little double dagger sign to say this is the transition state. It's on that delta G graph, right? It's like this point here. It's the highest energy thing that we have. So I could ask you, you know, what would you expect the transition state to look like at that point for this reaction, okay? And I could only expect you to answer that if you know the mechanism for the reaction, right? But I would generally ask that as a separate question. For intermediates, those are what you do when you are showing a mechanism. So those are any kind of halfway points between point A and point B. In the reaction that I have here, there is no intermediate. But if I have, say, an SN1 reaction, you end up with kind of these two humps, right? This point here is an intermediate. This is your starting material, this is your product. So an intermediate is not something that can actually be isolated because it's not stable. It usually has a charge on it somewhere or something like that. But the starting material and the product do sometimes have this kind of in-between point, and we call that the intermediate. And some reactions have lots of intermediates, some reactions have no intermediates. All reactions have a transition state. If you do have, you know, if a mechanism question has an intermediate, I do expect you to show them, or otherwise you didn't actually show the full mechanism, though. I hope that makes sense. Let me know if that makes sense. Okay, so based off of pKa values, right? Means I wanted you to know the general pKa values. So let's see. So remember that for a strong acid, like HCl, right? It has a conjugate base of Cl minus. Cl minus is a very, very weak conjugate base. It's a very, very weak base, period. If I have something like water that is not a strong acid, its conjugate base is hydroxide, which we know of as a strong base, right? So if you have a really strong acid, you get a weak conjugate base. If you have a weak acid, you generally get a pretty strong conjugate base. So based off of that, if you're looking at hydrogen gas that has a pKa value around 40, we have water, which has a pKa value of around 15, ammonia, which is in the 30s, around 35, and then looks like methanol, which is around 16. So that means that this here is the strongest acid in this order. And so for the bases, it would be the opposite order. The conjugate base of that, hydrogen hydride, would be the strongest, followed by NH2 minus, followed by methanol, technically methoxide, followed by, oh shoot, started going in the wrong order, I'm sorry, hydroxide. Once you get a really good understanding, I spend way more time on acid-base chemistry than I probably should, but once you understand it, it helps with a lot of stuff, you know. It's one of those fundamentals that can carry you pretty far. All right, guys, we've been on here for 1 hour and 20 minutes. One more question. The exam's already made and printed out, so I wasn't sure if I'd have time to do it this weekend since I went out of town. So it's actually sitting in my inbox at work. So no more questions? Well, we've had a lot of questions. Look at all these. Goodness gracious. Hopefully this was useful for y'all. I'm questioned out. That's a good place to be in, actually. That's much better than the alternative, isn't it? Oh my gosh. I have so many more questions. Fantastic. Well, thanks for y'all for showing up tonight and dealing with my weird issue with my webcam there for a while where I froze like this for far too long. And I will still have internet, you know, capabilities tonight. So if you run into a problem, my phone is dead, as now Google's sending me a new phone. But if you take a picture of what you're working on with your phone, you can send that to me, and I'm more than happy to, you know, look at it and see how you're doing. And other than that, I'll see you guys in the morning. Anything else? Start closing out my screens. I don't need to save any of this. Technically, YouTube saves it all for me. Ooh, 2 Ks on the thank you. You're welcome, Brandy. I'm glad you guys are finding this useful. With that, I will say good night.